Welcome to another inorganic chemistry lesson. In this session, we'll continue to talk about oxidation reduction reactions. Last time we discussed how to write have reactions, which compounds or ions are oxidized and which are reduced. If you haven't seen that, I'll leave a link in the right top corner. This time, I will show you how to use have reactions to balance chemical equations. Let's look at the reaction where sodium reacts with sulfur. In this case, we get sodium sulfide. Let's quickly write the oxidation states of each element in the reaction. Now it's time for have reactions. Pure sodium lost an electron and became a sodium cation, so it was oxidized. Sulfur, on the other hand, gained 2 electrons and was reduced. Now, how to use this information to balance the equations? The first thing you need to do is to even out electrons in both have reactions. The easiest way to do this is to swap the numbers you wrote in the have reaction and multiply each reaction by that number. For sodium have reaction, it would be 2, and for sulfur have reaction, it would be 1. Now, when multiplying have reactions, you multiply each compound and electrons from that number. In this case, we get 2Na, reaction arrow, 2Na+, and 2 electrons. For sulfur's have reaction, nothing's changed because we multiplied by 1. Now we got the total number of how many atoms must be in the balanced reaction. So in balanced reaction, we must have 2 sodium atoms. And because of that, we write 2 as a coefficient in the reaction. Next, we must have 2 Na plus ions in the balanced reaction. If we look at the reaction, we can see that we already have them, so no coefficient is needed this time. What about sulfur? Well, we must have 1 pure sulfur atom and 1 S2- ion, and that is what we have in the chemical reaction. On to the next example, where copper 2 oxide reacts with aluminum and produces pure copper and aluminum oxide. Let's write the oxidation states of each element. Copper in copper 2 oxide is 2 plus and oxygen is 2 minus. Because aluminum is a pure element, its oxidation state is 0. Also, same goes for copper. Aluminum in aluminum oxide is 3 plus and oxygen is 2 minus. Now have reactions. Copper gained 2 electrons and became a pure element, and a pure aluminum lost 3 electrons and became an aluminum cation. And because of that, copper was reduced and aluminum was oxidized. Now, to even out electrons, we must multiply copper have reaction by 3 and aluminum by 2. Once again, we get new have reactions with a number of atoms in the balanced reaction. So let's look at our new have reactions and use them to balance chemical reaction. In a balanced reaction, you must have 3 copper cations, and because of that, I write 3 in front of a copper 2 oxide. Also, you must have 3 pure copper atoms. For pure aluminum, we have 2 atoms, and lastly, for aluminum ions, we also have 2. But because there's already 2 aluminum ions in the reaction, we don't need to write anything. Now, the reaction is perfectly balanced. Before we go to the more difficult examples, let's look how to balance the reaction where chlorine reacts with oxygen, where we get chlorine 7 oxide. Let me quickly write oxidation states and have reactions for this example. Okay, now let's even out electrons. We multiply chlorine half reaction by 2 and oxygen by 7. The last thing to do is to write coefficients in the actual reaction. For chlorine, we need to have 2 atoms before and after the reaction, which we have. And we must have 7 oxygen atoms before the reaction and 7 after it. To get 7, we need to write 7 halves in front of the oxygen. Usually, we do not write fractions when balancing reactions. What we can do is to multiply all coefficients by 2. So in this case, we get 2Cl2 plus 7O2, reaction arrow 2Cl2O7. And now we have a balanced reaction. As I mentioned in the last video, this method is used for more difficult reactions. So let's do a few of those. The concentrated sulfuric acid reacts with sodium and produces sodium sulfate, hydrogen sulfide, and water. Let's write oxidation states for each element. Hydrogen in sulfuric acid is plus and oxygen is 2 minus. Now, how to know what the oxidation state is sulfur? Well, you just need to remember that there are the same amount of pluses and minuses in the compound. We multiply subscript with charge, and because of that, oxygen give us 8 minuses. Hydrogen give us 2 pluses. So we have 2 pluses and 8 minuses. So sulfur should be 6 plus. To even out positive and negative particles. Next, we have pure sodium, which is 0. The sodium ion is plus, oxygen is 2 minus, and sulfur once again is 6 plus. 8 minuses and 2 pluses, right? Then we have hydrogen, which is plus, sulfur is 2 minus, hydrogen is plus, and oxygen is 2 minus. So our half reactions should look like this. Sulfur gains 8 electrons and becomes S2 minus, and sodium loses an electron and becomes sodium cation. Now, to even out electrons, we must multiply the first half reaction by 1 and the second one by 8. We get 8Na, reaction arrow 8Na plus 8 electrons. Now let's write coefficients in the reaction. In front of pure sodium, we write 8, and in front of sodium sulfate, we write 4, because we already have 2 sodium atoms present. In front of H2S, we don't write anything because we're supposed to have only one S2 minus ion. And the same can be said about S6 plus. However, there is one rule. If the same oxidation state appears more than one time in the reaction, we can't use a half reaction to help us balance that particle. Sulfur 6 plus appears 2 times in the reaction, so we can't use half reaction for this ion, and we need to balance sulfur before the reaction ourselves. After the reaction, we have a total of 5 sulfurs. So that means we can write 5 in front of H2SO4. What about hydrogens? We have 10 hydrogens before the reaction. And after reaction, we have 2 hydrogens in H2S and 2 in H2O. We can't write the coefficient in front of H2S, because in half reaction, we have only one S2 minus ion. So that means we can only write the coefficient in front of water, and that coefficient is 4. Now we have an equal number of hydrogen atoms as well. This method only gives us information about some of the particles in the chemical reaction. The rest we need to balance on our own. On to the last example, where potassium permanganate reacts with a hydrogen chloride. Let's quickly write the charges of each element. Potassium is plus, oxygen is 2 minus, manganese is 7 plus, hydrogen is plus, chloride minus, potassium plus, chloride minus, manganese 2 plus, chloride minus, chlorine 0, hydrogen plus, and oxygen is 2 minus. Now have reactions. Manganese gained 5 electrons and became manganese 2 plus ion. Chloride ion lost an electron and became pure chlorine. Now, to even out the electrons, we multiply the first half reaction by 1 and second one by 5. Like always, we get how many atoms we should have in a balanced reaction. And now, let's write the coefficients. Let's start with Cl-. Remember the rule I wrote in the last example. Chlorine anion constantly appears throughout the reaction, so we must skip it. We must have 5 pure chlorine atoms in the balance equation. But because we have already 2 of them, we can write only fraction, which is 5 halves. Now we can multiply all reaction by 2. So now we have 5Cl2. What about manganese? Well, half reaction shows that we must have 1 on each reaction side. However, we multiply the reaction by 2, so we write 2 in front of KMnO4 and 2 in front of MnCl2. Now, after we used all available information, we must balance the equation by counting atoms. We have 2 potassium atoms before the reaction, so we write 2 in front of KCl. Now we can calculate the total number of chlorine atoms after the reaction. 4 from MnCl2, 2 from KCl, and 10 from Cl2, so it equals to 16. Now we write coefficient 16 in front of HCl. And lastly, coefficient 8 in front of the water. At last, the reaction is balanced. And that's all for today's lesson. Like always, I leave few exercises for you. Please like and subscribe for more chemistry content, and see you soon in the next lesson.